Hydrogen in mobility, a false good idea? Transport and mobility account for around 24% of global greenhouse gas emissions. And this is mostly due to the fuels. Solutions to get rid of fossil fuel engines must thus be developed and deployed. Can green hydrogen be the solutions to do so? Yes and no. For all heavy transports, such as trucks, buses, maritime and air transport, green hydrogen and its derivatives are particularly relevant. For light mobility, and in particular for personal cars, electric propulsion tends to be the best approach. Let me explain why. Let's consider a traditional internal combustion engine for a car running on gasoline. Suppose that at its source, and underground, oil has an energy capacity of 100. After extraction, delivery, and refining, this drops to 86 points. And after use in the combustion engine, it literally plummets to 17 points. So as can be seen, in terms of power efficiency, fossil fuel for light mobility is very inefficient. In terms of CO2 emissions, the situation is quite similar. If we take into account the vehicle manufacturing, the oil extraction and refining process, and its combustion in the engine, an individual car approximately accounts for 54 tons of CO2 equivalent over its entire life cycle. Let's look at a second case now. A personal car powered by green electricity produced by wind power. Again, at the source, the wind turbine, the energy capacity is 100 points. It will lose 8 points during transport and distribution, and then another 9 points during battery charging, leaving us with around 83 points. This battery will deliver only 77 points to the electric motor, which itself converts it into 69 points of mechanical energy. And regarding CO2 emissions, considering the manufacturing of the car, the manufacturing of its batteries, the generation of its electricity, the electric car emits around 25 tons of CO2 equivalent over its life cycle. In summary, electric vehicles lose 3 times less energy capacity compared to traditional vehicles, and they emit twice as little CO2. And now, what about green hydrogen cars? Again, let's take wind power as the source of green electricity, with its 100 energy points at the source. We'll first lose the same 8 points during transport and distribution, and then to produce green hydrogen, we consume 21 points in the electrolyzer and 7 more in the compressor, leaving us with only 64 energy points. Then the fuel cell costs 34 points, and finally, the electric motor consumes 3 points, ultimately delivering only 27 points of mechanical energy. For CO2 emissions, the whole process results in a total of 37 tons of CO2 equivalent per vehicle over its life cycle. Now let's keep the order of magnitude. From the 100 initially, the thermal engine will deliver around 20, the fuel cell plus electric motor around 30, and the full electric car around 70. This gap is huge, and it's explaining why the electric vehicle has taken the lead for passenger car. Hydrogen-fueled passenger car can make sense when the time for charging or the heavy load of batteries deteriorate the economic performance of use. This clearly confirms my initial point. Even if in specific 24/7 operating applications like urban taxis or forklifts, green hydrogen's rapid refueling ability make it more cost-effective than electric, and its zero CO2 emissions make it more environmentally friendly than fossil fuels, electric vehicles remain the top choice for individual mobility, outperforming green hydrogen and especially fossil fuel engines. But what about heavy transport by trucks, cargo ships and airplanes? These applications remain at the heart of European objectives to achieve carbon neutrality. This is Green Deal, this is Repower EU. For those, green hydrogen-based propulsions makes perfect sense. Container ships, for example, are inherently very energy intensive. Their business model is to transport maximum cargo over very long distances with a relatively limited time frame. Powered by fossil fuels, they emit a lot of CO2. And for them, switching to electric power is not realistic due to weight, size, and recharging time constraints. And here, green H2 and its derivative, e-methanol or green ammonia are excellent alternatives. Engines able to accept these fuels already exist, and these new fueling solutions can be used by current boats for the same distances or capacities. They offer similar speed and refueling times, and having one huge advantage versus fossil fuels, they drastically lower CO2 emissions. The same reasoning applies for aircraft. Electric airplanes are not an option to replace traditional planes, maybe except for very little ones, given recharging time, distance capacity, and left cargo capacity. You know, using H2 has been explored in the 60s, but the storage of compressed or liquid hydrogen is so complex that it would require huge changes in airplane design and airport infrastructures. However, the use of synthetic kerosene, made from green hydrogen and captured CO2, is seen as a perfect alternative. Recharging times, distance, and cargo capacity remain the same, and CO2 emissions are drastically lowered. Moreover, transitioning from conventional kerosene to eSAF can be very straightforward, as it requires minimal modifications to aircraft and airport infrastructures. Therefore, what is preventing green hydrogen and its derivatives from being deployed immediately and limiting by this way greenhouse gas emissions of transport and mobility? Price, of course. These carbon-free fuels are still much more expensive than fossil fuels. And this is where Rely comes in. We are committed to developing technological solutions to reduce these costs and accelerate the deployment of these sustainable options. At Rely, we call this bridging the gap. How can this be achieved? We will come back with another video in the coming time. See you soon.